I'm going to talk about matrix normal distributions. This talk will be in two parts. The first part will be about variational inference, variational learning with matrix normal distributions. The second part will be about Riemannian optimization and our recent progress on applying it for matrix normal distributions. So, as the same way previous seminars went, I do the same slide there. So what we're doing, we are training some neural network that has millions of waves. We have this prior distribution, we have this likelihood. So we want to obtain the posterior, but we cannot get the exact posterior, so we are approximating it with some Q. Okay. Ладно. So we
have to point with your finger.
Awesome. So we're approximated with some function q. Then when we want to get some answers for our data, we just get several samples from our approximating distribution and average it. So what are our choices for the approximating distribution? So, as we have a very large parameter space of millions of waves, we don't have much choice over there. Like we have our classical normal distribution with independent components, but it's too simple and it's just not very good. Then we have normalizing flows, but it's cubic. Regarding the time complexity, so it's not okay for us, but there's some work like Fjord that was presented there several seminars ago, and I don't know if anybody has applied it to neural networks. So then we have some implicit methods that depend on training some discriminator, which also doesn't work because how do you train a neural network that has millions of inputs? And then we have hierarchical models like semi-implicit inference or some kind of a normalizing flows where for example, we only apply normalizing flows to parameterize some of the components of our simple distribution, like normal, but we're still to train, and in the case of the semi-implicit distributions, it's very possible that the mixing distribution just collapses to something simple, to the delta function, so there's no gain in using the semi-implicit distribution at all. So what we propose is the matrix variant distribution, like the matrix nomad distribution. What is it? So the probability density function isn't very speaking of itself. So an easier way to describe what it is just to say that if we have some matrix X that is distributed according to the matrix normal law, then it means that we have some vector X, vectorization of X that is distributed normally, but with a special structure imposed on the covariance matrix. That means that if you have like a zero mean, rows are independent, columns are independent of rows, and U basically parameterizes the covariance matrix of rows, and UB parameterizes the covariance matrix of the columns by themselves. So we can model the covariances of the rows and the columns by themselves, but we can't model dependencies between them intermediately. So where we have seen the MN distribution first, we have seen that in the Kefek paper that we actually can observe some independency, that we can compose the Hessian using two independent parts, using the Kronecker structure. Then we've seen the scalable Laplace approximation paper. We have seen that it is a very good approximation to the actual posterior. Then we have seen the upcoming catastrophic forgetting paper. We have seen that we can get very good priors when using matrix normal distributions. So also I want to
understand right that this matrix normal distribution is less flexible than just fully factorized Gaussian.
Yes, but it's actually tractable, so it's kind of close to it, and we show that it's not much better than the fully parameterized.
I thought fully factorized.
Yes.
Mm-hmm.
So it's much better than fully factorized because we can model covariances, but still, compared to the fully factorized one, we have the same order of parameters, which is very interesting to me.
It seems that we have a much less number of parameters than in the case of fully factorized Gaussian.
Now we have like the full covariance matrix for the rows, the full covariance matrix for the columns, like we have the n squared, and then fully factorized one, we have the same order like nm.
Mm-hmm. Okay.
So another motivation where we should use the matrix normal is this regression problem. For example, we have some data set, we have some inputs, we have some outputs, they are both real, they are both multivariate, we have some normal prior, we have just our linear prediction, we have our likelihood. And what we see is that the exact posterior for this problem is matrix normal. Even though like the priors for the weaves were just regular normals. So if we have used variational inference for this problem with our regular fully factorized normal distribution, it will have failed because there is some clear dependencies between the rows, which it wouldn't have caught. But our exact posterior with matrix normal does. So the first thing we want to do when we get this matrix normal is to learn how to parameterize it, at least how to store it. Many papers opt to using some low-rank approximation, like some diagonal matrix P plus UV transposed, but I don't see any problems using the full parameterization when we optimize the Cholesky factors, but with some special structure that allows us to, for example, compute logarithm determinants quickly. Like there we use two covariance matrices that are Cholesky factorized. We optimize A and B, which are by themselves Lagrange triangular, and the diagonals are parameterized by the logarithm of some matrices. So this gets us unrestricted matrix normal distribution. This gets us quick reparameterization tricks and some future work on the Riemannian optimization that we could get there, since we have a lot of structure. But that's for the last part. So to apply variational learning with this distribution, we must know three things. First one is obviously the reparameterization trick, how to perform it. The second one is how to perform the local reparameterization trick. And the third one is how to compute the chiral divergence between our approximation and the prior.
Can you just sample it and get the results? You really do not need to compute it. You need just an randomized estimation.
No, but if we can compute it, that will be even better. Because that
I
will use the variance of stochastic gradient.
I can say so. Really, it works approximately the same.
Mm-hmm. Okay.
Just based on my experience.
So regarding the regular reparameterization trick, it's very simple. Like we have some matrix composed of independent random noise. Then we just do this, and voila, we have the matrix sample from the matrix normal distribution, which is kind of nice. So the next step is to get the local reparameterization trick right. So we have some matrix W from the MN distribution, we have some fixed vector X and we want to obtain some sample from the resulting output distribution WTX. So it turns out that it's also normal. Moreover, it's matrix normal too, but with one core reduced to one-to-one size. So it's quite easy to get the localization trig too. So we just obtain this scalar, we just obtain some noise, multiply it by our output covariance factor, and there we go. For the covariance divergence, we apply the same formula as we apply for other normal distributions, like the ratio, the logarithm of ratio of two log depths of covariance matrices plus trace of b minus 1a plus some quadratic form on with the mean matrix. So if we substitute further, we get like to this point. And the last thing that bothers us is this logarithm determinants, which by our structure computes linearly without any need to opt out to some SVD or other decomposition. So the whole thing computes just linearly to the number of elements of our matrices. So that's good. Then we proceed to the problem that we are actually solving. Today we're solving the art sparsification, moreover the group art sparsification. So we have our data set, we have our likelihood, we have some parameterized by some hyperparameters. So we want to find some posterior and want to optimize with regards to alpha. So we obtain our optimal alpha star, and when the prior is the product of independent normals, it's called the art prior, and the whole model is called the art sparsification. So the first thing we do is that we write down the elbow. It's pretty regular. Then we assume that we use our regular independent normal variational family, and we use the arc prior. With that we can find the optimal alpha star. We substitute it back to the elbow, and we conclude that we have our regular likelihood plus some regular lecture. It was before the divergence. And we can optimize it with regards to mu and sigma. But what if we want some structured sparsity? Because if we just remove random parts from our matrix, we can't use it actually in the software because there's no way to effectively use these sparse matrices. But we actually can use it, some sparsity when it has some structure. For example, if we remove the whole neurons, if we remove the whole inputs. So the easy way to modify the art technique for the group specification is just to impose some structure on our prior. So after it becomes the matrix normal distribution, which is quite nice. But there comes the trick that we can't obtain the optimal values of our tau and gamma. So we need to optimize it with other parameters as well. If we do that, we come to the experiment section. So the first experiment is pretty classic. We have some NIST, we have some fully connected neural network of 5 layers, and we just do some sparsification. As we see there, the matrix normal distribution actually obtains a bit better test prediction accuracy and much higher compression ratio. So we can sparsify it like in 70 times, whereas with the approximation we could sparsify it in like 40 times.
What was the baseline?
So the baseline was the diagonal covariance for the variational family. Like it's pretty similar to the variational dropout technique, which is used as the baseline in most of the papers. So I thought it would be.
The prior is also fully factorized Gaussian.
Yeah. Yeah. So that part is about just unrestricted sparsification, but then we would just come to the group system.
Can we say that the relative improvement we observe here in comparison with the baseline is achieved due to the fact that you have a less number of hyperparameters than you would have in the baseline, in the diagonal model?
Now we have just the same hyperparameters because like in both we have our regular normal distribution as our prior, and we tuned just those. So it's not the group specification yet, it's just regular.
Do you have some intuition why one model is better than another? Because it's kind of, if you have less flexible distribution, I can believe that empirical bias would lead to more sparse solution. But if you have much more expressive distribution, I cannot believe that empirical bias would work better with more expressive prior. It's kind of really look the same, and I really want to get the reason why kind of matrix normal model works much better than just diagonal.
So it's probably about the fact that we have a little motivation that the exact posterior looks like matrix normal in the linear model, but
is it just linear model? Or is it deep neural network?
it's a deep neural network, it's like 5.
But okay, what is the connection between linear model and...
So imagine that it's just one of our layers, and if we have this in the linear case, why won't we just look at it in the deep neural network setting? Like also before we have seen that in the previous papers there was some clear motivation that using this Kronecker factorized structure clearly helps to model the neural network wave distribution, like in the scalable Laplace approximation that we cited several seminars ago too. It worked clearly better than the regular one, so I think it's the same reasons as there, because our linear transformations are just bigger, better modeled if we have the covariance matrices of the rows and the columns.
Yeah, but there is no direct connection between the quality of the posterior approximation and the level of sparsity. For example, I talked with Chris Lizos, who also works on compression and Bayesian learning, and so he told that when he tried to fit more elaborate posteriors, for example, multiplicative Riemannian flows, that compression just disappeared absolutely. So it is still not clear why this is the case.
I'll show you just a bit afterwards.
And can I ask one more question? Can we somehow check if this orange curve solution that is produced by orange curve is just a better optimum in your blue model? Like, isn't it just problem of some local optimum? Okay, you have more sparsity in orange one, maybe it's just better solution for blue model as well, for diagonal model as well.
So the least problem is quite easy one. So most part of the resulting clause at this point is just the cavity aversions. So it doesn't matter which is what the best quality is. Like there, I can say that it's much different, but we have like different elbows, different compression qualities, and so on. So I guess that in the further experience I will be able to show that it's about the better approximation, and consequently it's just a lower K values.
How ARG effect is achieved here? I did not still understand. So I understand how we can achieve it when we have a diagonal matrix for the prior, but when we have a matrix normal prior distribution. Then what should happen with the hyperparameters in order to achieve sparsity? and whether it will be group sparsity or not, or just individual sparsity.
So we have the same hyperparameters, and if they go to the infinity, that means that
But no, they're not the same, they're different. Because these are not the parameters of the diagonal matrix, right? Can you please switch back to the formulation of your model?
No, they are the parameters of the diagonal matrix because the prior, in both cases, the prior is the fully factorized Gaussian. Right?
Then what is the difference?
The posterior approximation.
Okay.
So basically, just change this part to the matrix normal one.
And you achieve better compression, but worse accuracy, at least in the end.
Not much better.
Although
It just repeats
It's
heavily.
But I'm still sorry. I'll ask my last question again. Okay, you have your model with matrix normal posterior distribution. You can compute mean weights of your posterior, variational posterior. Then you can compute variances of every single weight. Just at least fully factorized approximation of these variances. So independent variance for every single weight, and independent mean for every single weight. Then you can edit more simple, fully factorized Gaussian variational approximation with this mean and with these variances. These means and with these variances. Then you can compute just objective of your blue model on these weights. And I'm wondering if the blue model is bad just to poor local optimum. So can we say that if we just take solution of orange model, plug it into blue model, and attain better value of loss function?
I don't know. We just
Because
need some
it's kind of
theory.
very interesting. Why does it happen?
I don't think that this is the case because if you compute the marginal variances of a highly correlated distribution, you would severely overestimate the variances. So I think it would just blow up.
Again, this is also quite a speculative statement. I'm afraid that you cannot be sure until you check.
Yeah.
Although intuitively I agree with our professor, but still not 100% sure.
Okay, so we check that afterwards. So then we come to the fashion list. It's much harder data set that, like, obtaining 95% over there requires no less than ResNets. So it's quite a good result to get like 92% with something as simple as like 5-layer CNN. So that's still a regular sparsification. And you see there, we achieve the similar results, like we have a bit better test quality, we have a bit better compression ratio, and also I can show like what we get there. Like just because we used our structured posterior, we already can observe structure in the widths that we get after loading. Like clearly there's some rows and columns that were sparsified, even though we haven't specified it in the model. Like the prior is still independent normals, the posterior is a matrix normal.
How do you apply the matrix Gaussian posterior to convolutional kernels?
So, as many know, that convolutional neural networks are actually computed via the matrix product. So basically, you can just reshape the widths of our layers. So then multiply it by some specially generated matrix, and there we go.
But the parameters in this matrix are highly shared between each other. So I don't see how to implement this.
Now we just, if we have some weak matrix, we just shape it, and I don't see how to connect it. Yes, I guess.
So can you maybe write it down? Because like you just reshape the convolutional kernel into a matrix, like width by height by number of inputs.
How do we turn it on?
Yes, the same as this standard.
And how is it done in Internet?
Output times everything.
Okay. Yeah, that makes sense.
Okay.
And is it possible to perform local reparameterization?
Kinda.
So what about?
What?
Not possible.
Yeah.
So the next one is without any sparsification, just to do some Bayesian running. We have just some ensemble, we have some elbow, but we can tune any hyperparameters. They are just set to some constant, or the same one for the all layers. So what we see there is that on the VGG-like network that has several, like 100,000 of parameters, 11 layers that we get, but we can obtain 2% improvement in both test quality and in output.
And wondering how is it compared to non-Bayesian model? Like VGG is pure VGG is 2000 benchmarks.
It should be 93.2.
Yeah.
It's 93.2 if we actually do some augmentation, if we do some mesh normalization, if we get much wider network.
Yeah, it's something like.
Yeah, but now it's not needed.
Bayesian was not needed.
So this is actually just plain several convolutional blocks stacked on each other without anything else, without augmentation, without batch norms, without dropouts.
But it's still interesting to see comparison with
Yes.
with non-Bayesian model in this setting because you know it can differs a lot.
Mhm.
And I have one question about the coefficient in front of curve divergence. Have you used any?
No,
Just
yes,
one. Yep.
yes, without any.
From the very beginning.
From the very beginning, like no annealing, no nothing.
Maybe you should play with it as well.
Yeah.
Maybe if you start with a small dose of this coefficient and then gradually increase it up to 1, you could get better accuracy.
Yeah.
Because the first network needs to learn, and then you may sparsify. If you start sparsifying from the very beginning, you may simply underfit.
So that was a problem of the previous networks. So when we try to solve it, like
But
Can we
we
get some-
cannot say that it's not problem in this case because we do not see any reference.
Mhm.
Like maybe we have the same problem here.
We see that your model still underfits. And it's still performing below the baseline.
Probably underfits. It's not exactly.
Underfits.
so
Underfits probably.
Probably,
Not
yes.
exactly.
so just for the reference, like later in the slides, I give an example of the network that obtains 88% test quality, which is kind of nice for the Bayesian network. So that's just still a toy network, I guess. So yeah, then we proceed to the group specification. That's the slide over there. Also, we get another line that's MNDiag. It's just what we get if we use not just connector product structure, but we also add some diagonal metrics. So we get,
It makes the situation only worse.
Yeah.
yeah.
But accuracy gets better.
No. The best accuracy is achieved using just matrix normal distribution.
Can you show previous slide, please? 82 here,
It's
and
different
then
than
on the next slide, and 84 here.
It's
Something
It's
goes
different.
Yeah, but can you see an accuracy? And can you see that accuracy is 2%
what
more
is again?
Yeah,
than
because
this one than previous one? And it's really strange because we kind of put much more concentration in our network. Maybe it's just yesterday of your method.
So that's why it's still a bit easier problem to learn. So yeah, that's not the case. And there are 2 points over there. Like that, there was no specification, and there is specification. Like we can make our elbow much better because we optimize our hyperparameters, and the elbow is becoming higher. Then we just fixed it with some constant.
So here it is just the standard Gaussian triad, or what? Like on the previous slide.
Yeah, it's
What is the section theorem exactly?
Yes, the prior is just some fixed normal distribution with some alpha squared as the covariance for all the layers.
Okay, and then the second slide?
And then in this slide we use the group R prior, so we actually sparsify something.
But what was the prior exactly?
The prior was this one,
This
the
one.
second one.
Uh-huh. And what was the compression rate?
So that is on the next slides.
Uh-huh.
So what we have there is three models, the diagonal one, the matrix normal one, and the combined one. So as we see, man doesn't have much better compression rate than for the diagonal matrices, but it's still fixable without losing in most any accuracy if we combine it with the diagonal
Can
one.
you please divide
What is
annotation?
one?
I cannot.
Okay,
the
so
paper.
in each section there, we have three rows. The first one is the total number of thousands of waves that we have on the layer. The second one, the W, is how many weaves are left. And the third row, that's percent, is just how much weaves we have dropped throughout the optimization.
But could you also compute the number of neurons you could drop?
Yeah,
As far as I
that's
understand?
the next slide.
Okay.
So it's quite interesting to continue working on the man plus diagonal piece, since it can provide us with a both better compression rates and better test accuracy. So that's the case.
But as far as I understand, the best compression is achieved in the case of diagonal
Yeah,
posterior, not in the case of matrix
But it's
normal.
not very useful.
but it still has like
Yes, yes,
80
yes.
compressions.
It's okay for compression,
Mhm.
not for kind of acceleration.
Mhm. So the next slide is what we get if we upscale the network 4 times. Like we had 60,000 waves and now we have 2050. So there are 3 sections. The first one is just we remove any zeros we have in our width matrices. Second one, we just remove the rows of our matrices. Like if the row is fully composed of zeros, we remove it. And the third one is the same for the columns.
Wait, so is this the actual number of weights in the network, just 250,000?
Yeah. But it still achieves like 88%.
Oh, okay.
So that kind of counts, I guess. So at this point, I end my first part, and then okay.
What is like row only or column only is the neuron sparsity?
Can you repeat the question, please?
Where is the neuron sparsity? Is it a row only or column only?
I guess it's column only. Yes.
I'm not sure. From our point of view, you may either consider incoming batch of the weights or outcoming batch of the weights.
It's like
In both cases, if either incoming batch or outcoming batch is zero, you may remove the corresponding neuron. An incoming batch of the weights corresponds to the, say, row, and the outcoming corresponds to column, or vice versa.
Isn't it like not very high sparsity?
But the network is very, very small.
What?
The network is very, very small.
But here it was, the width was extended 4 times.
But it's still extremely small.
Yeah.
It's extremely small. Like that's probably the case over there, but still, if we like multiply 3 over 4.5 and multiply it by the column on this sparsity, we still get the 50% compression.
And can we compare this with alternative techniques?
Yeah.
So I should try to learn.
For example, with the diagonal variational approximation and with the group-wise ARD prior.
So we tried actually to learn the diagonal one. That couldn't just learn, it just diverged from the start. So I guess it should have been trained and specified just only after we trained something to start from. But with the matrix normal, we could just proceed training from scratch, which is kind of a good
And
thing.
what about like pruning techniques?
Like we have our leaf matrices, we have our alphas, so why not just...
I mean, it's quite difficult to understand are these numbers good or bad because we don't have any baseline here.
Yeah.
And like without baseline, these numbers are not very good, at least for me.
Richard, I have one more. Probably you can contact to Dima Molchanov or maybe Valera Kharitonov. As far as I know, they have a really high quality implementation of
Maybe not very high quality.
with more simple priors, like sparse variation dropout, like automatic relevance determination with normal priors for deep neural network. And you can use the PyTorch code as a baseline for your work.
Okay.
Maybe you can just change the size of architecture and then see how it works.
Okay. So, that's the end of my part.
Let us thank the first speaker.